Good evening, everyone. I hope you're still doing well, making progress. Uh, we will be concluding our lecture series of lectures tonight with the last two sections talking about normal distributions, both in 12.4 and 12.5. So this last content's all related. Then I will have a practice test for y'all, and I will do some videos working through that so we can take a look at that. As far as timing, the May 22nd, let's just put it that way. That's kind of the last day. We've gotten a 2-week extension. So next week is officially finals week. For us, it actually is like a 3-week extension because we were supposed to have the final exam tonight. I don't know about you, I'm not ready for it. So good thing we're not having it. So we're going to, we still got 3 weeks. We've got the extended time to get everything done, but you can get it done earlier too. So over the weekend, I will be posting a practice test for the final as well as the final itself. So then you'll be able to prepare for it. And then when you're ready, take it. You could be done next week if you'd like, or we've got a couple more weeks to be able to work through everything. Okay, so now let's talk about the normal distribution. And let me see, what is it, come back here. We'll be using this. This is actually the e-text, but that's what was causing the problem. Okay, so now we're back on track. We're going to do the normal distribution. And the word normal doesn't really mean that it's regular, like the way we would use the word normal, although it kind of has that, but it is a specific distribution of data, is what we'll say. So here's some of the objectives. We're going to say what is a normal what makes a normal distribution normal. We're going to see that there's a particular rule. There's 3 measurements, and these are percentages. So 68%, 95%, or 99.7%. That's kind of a rule. It's a general rule that we're going to work with. Notice we're going to use it as well. So one of the things you'll kind of remember these 3 numbers because they're pretty much going to be the answer to the questions we're going to be faced. One of these 3. Or potentially half of them. Some of the questions only get half of this area. We're going to see those as we go through those. Talk about standard deviations, which we started talking about the last thing we did, looking at something called a z-score, standard score, and percentiles and quartiles, margin of error, which is a good thing to know about because anytime we do a study, they'll give us 25% of the people will do this, but not exactly 25. There's a margin of error with everything that's measured. Okay, and then we're also going to look at some distributions that are not normal, and there's a lot of things that are not normal distributions. So, what is a normal distribution? Well, if you've heard or thought of the bell curve, that's what the normal distribution is. It's a bell shape. So this one down here, D, is a very nice normal distribution. One of the factors it has is that the mean, the median, and the mode, notice the frequency would be the mode, are all equal, and they're all right in the middle. So that's kind of what makes it that's one of the qualities a normal distribution has. Now notice over here, there's maybe just not enough data here because it's a little bit to the, we'd say, it's got a little bit of a skew to it. This one also looks like it's kind of skewed, but it's just the more data you get for something that's normal, the more it will look like this smooth bell curve over here. So more and more larger and larger sample size. Okay, so this would be like the population, everybody. So the shape is always the same, but there could be, so all 3 of these are normal distributions, but they have different standard deviations. what we're going to see is we're going to get a measurement that will standardize the standard deviation. So the spread, because again, mean, median, mode are always right there in the middle, and it's symmetric about that. But these three would be normal, but when we standardize it, they're all going to look like this one and pretty much in the middle. Okay, so when we have the standardized normal distribution, what we do is we look at the standard deviations, and that's sort of what marks them. So here's the mean, 0, right in the middle, and we'll talk about how that happens, how we get that as 0. One standard deviation above to one standard deviation below is going to give us 68% of the data. So 68% of the data are in these measurements here. Why 68? It just is. Okay, it's a natural thing that occurs, and there's different ways, and it has to do with probability. And a normal distribution typically comes from something that is created from having a lot of different factors involved, something like genetics, and that's why the height of people is generally normally distributed. Shoe size is a normal distribution. So things dealing with genetics typically will have a normal distribution, whether it's humans, animals, fruits, but that's where it comes from. Okay, so it's just take a lot of measurements, and what they found is 68% of the data will be right between one standard deviation below to one standard deviation above. And notice when you're below the mean, that's where you get the negative scores. Positive scores are above the mean. Okay, and so we'll keep going. So when we're from 2 above to 2 below, we'll do that with circles, we're going to have 95% of the data. Again, why 95? It just is. And it's something that happens from nature. It's dealing with the probability of things happening. This is just how it happens. It's something that's natural. Why is the sky blue? Well, there's a scientific reason for that as well, but there's certain things. This is just how it happens, and as we saw, that was discovered this way. And then when we go all the way out to 3 below to 3 above, we're going to include 99.7% of the data. I mean, it's just a little bit's left over that could be in what we would call outlier mode. So maybe, way out here or maybe down here. So 99.7% of the data is within 3 standard deviations, 3 below to 3 above. Again, that's 6 divisions, but so these are the 3 numbers we're going to use. We're going to do some calculations, and we'll see the answers to most of our questions when we're looking at percentages will be one of these 3, 68, 95, or 99.7. Okay. So here's an example. Male adult heights in North America are approximately normally distributed. We have a mean of 70 inches. It's a little higher than me. And standard deviation of 4 inches. So the standard deviation is 4. Find the height that is 2 standard deviations above the mean. So they do it here, but just think, we've got 70. We're going to go 1, 2 standard deviations. Well, how much is a standard deviation? It's 4. So we go 4 plus 4 more, right? So 4 would get us to 74. 4 more gets us to 78. Okay, so they just took 2 times the 4. I like thinking of it in this fashion here because you actually see the 2 steps that are taken, 2 standard deviations. And you see, while we were doing it, we also calculate how many is 1 standard deviation. So there's 1 standard deviation, there's 2 standard deviations. If we wanted to go below what we have done, we would have subtracted 4. So that would have given us 66, and then go 2 more below, go 2 standard deviations below. So there's -4, another -4, so we're at 62. So what can we say about the measurements from 62 to 78? There are 68, 95, 99.7. Which one? You got it. It's 95% because we're two below to two above, because this is really -2, right? This is -1 standard deviations. So this would be, now they didn't ask that question, I did, but I just want you to be able to think your way through these. Okay, so it's two above to two below. While we're at it, since they only asked for two above, they just asked for this part here, right? What percentage would be just two above? Wouldn't it make sense that since it's symmetric, it would be half of what is between the two? You're absolutely right. So just two above would be 95 divided by 2, which is 47.5%, I think. Yeah, 90 is 45, another 2.5. So yeah, so two above is just half of that symmetry, right? So we got this from here, from 0 to 2, that's going to be 47.5% of the data. Remember, we're doing frequencies. Okay. So here's what it looks like. Again, they've done it. You know, we went 66, 62, we went below. Here's 3 below. We went 2 above, they went 3 above, so then they're breaking it down. So yes, between one standard deviation, so between 66 and 74, we've got 68% of our people, of our population, whatever we're, males. So we could say 68% of the males are between 66 inches and 74. I am 5'10", so that's, I'm 70 inches. I never did the calculations before. I'm right in the middle. That's kind of cool. Just realize that, right? Because 5'10", 5 foot is 60 inches. 10 more inches would make me 70 inches. I am right at the mean. Cool. Half the heights are above and half below. A perfect place to be. Okay, so and you kind of see that here, right? So we could say there's 50% down on this end, 50% on that end. We're going to also cover these, but we'll just keep moving. Okay, yeah, just keep moving. So here's our rule, right? The 68, 95, 99.7. And why those numbers? They just are. This is how it happens, that it's a normal distribution. Other distributions don't have that. They have different numbers. Some of them are not symmetric, but a normal distribution, it will have that always. Okay, so a mean, let's see, so 68% of the data items fall within one standard deviation. So that's one below to one above. We did that calculation, so subtract one standard deviation, we're at 66. One standard deviation is actually -1 times 4. One standard deviation above is +1 times 4, so that gets us to 74. So there would be 68% of the population of males would be between these two heights. Okay, and we saw the 2 and the 3. Okay, one of the ways we have to be able to come back and compare to this normal curve is we calculate something called a z-score. Oftentimes, so in these problems, they're going to give you the mean. Now we could calculate, if we had the data, remember, we could calculate the mean, add it all together, divide by however many there are. But we're going to be dealing with things that have a large amount of data. It's tedious, so they're just going to give us the mean. The standard deviation, again, that's something we learned how to calculate in last class. We could take the data and calculate that. Remember, we have that calculator. It would actually even calculate both. It would give us the mean and the standard deviation. But for these problems, we're cutting past that. They're going to give us that. And then there's a third item they're going to give us. We'll do this as a triangle. That's the data item. So a particular person, like Little Crow, is 70 inches. I'm a data item. The mean was 70, right? Let's see. So the mean they gave us is 70 inches. Standard deviation is 4. And Little Crow, who is your data item, LC, um, LC is 70. So we put the data item of 70. 70 minus 70 is 0 divided by 4. That's 0. That's why in the graph you saw the mean in the middle, it's 0. That was a z-score. So they were getting us z-scores before they told us what a z-score was, because the mean minus the mean always going to give us 0. So again, but this, remember, this one here is Little Crow. This one here is just the mean of all the data. They calculated that. So it's always the mean, standard deviation, and then you get your piece of data. That will give you a standard score, and then we're going to see how we use that. We're going to give you a table. There's one in the textbook, and I put one here in the slideshow as well. I got a copy of it. Okay. So what these numbers down here, 0, 1, 2, 3, those are actually z-scores, right? So notice in all these problems, they give us the mean. So we're just going to go, the mean is 7. And they will also give us a standard deviation. How did they get that? They got all the data, plugged it in the calculator, and got it. So I like to just call that SD. There's also a Greek letter you can use. Sigma is also used. You might see it somewhere. It looks kind of more like that. That's a little sigma. There's a big sigma like this. Greek letters again, but sometimes they're used. I like to just use SD for standard deviation. So the weights of newborn infants are normally distributed. Find the z-score for a weight of 9 pounds. So what do we do? Again, I like rewriting this. The z-score is going to be data, so I'll just call it D, minus the mean over the standard deviation. So in this case, the data that they give us, this is our data, is going to be 9 minus the mean that they gave us, divided by 0.8. So this gives us 9 minus 7 is 2 over 0.8. And we'll just use a calculator, why not? 2 divided by 0.8 gives us 2.5. So we get a z-score of 2.5. And they show that right here. You know, here's 2.5 is there, and you can kind of see here's 8.6, here's 9.4. So it's right in there. They did it all for us. I'm not wearing my glasses, so it's kind of fuzzy for me, but I can see okay. You can probably see better than I can. And then they also give you one, what would a 6-pounder be? Well, a 6-pounder is below 7, so notice it's going to give us a negative z-score. We could do that, 6 minus 7 over 0.8, right? Just as simple as that. 6 minus 7 is a negative 1 over 0.8. So that's actually 10 divided by 0.8 is 8/10. Flip it, you get 10 divided by 8. Let's just do it this way. 1 divided by 0.8, yeah, 1.25. I could have read right there. So the calculation right here. So this, just remember that formula, put it in your notes. You're going to be using it a lot. But just make sure you get the order right, data minus the mean. And you'll notice because, when the data piece is smaller than the mean, we need to end up with a negative. When it's bigger than the mean, we need to end up with a positive. Okay. So they do all the calculations here like we did, 9 minus 7 divided by that, they get this, they get that, and it's positive. Okay. And you can write, I haven't seen it written this way, but yeah, z of 9. 9 is our data. So you can connect it that way. It's kind of a nice little shorthand. Again, I've been teaching for 20 years. I've never seen that. But, hey, live and learn. Okay. Another thing they use it on is intelligence quotients. And don't get me talking about IQ tests. We'll be here all night and we won't make any progress. But these are racially, gender biased. Um, you can read the research on it. It's the idea that intelligence, you're born with a certain intelligence ability, and from birth till death, it doesn't change. That means why get an education, right? We can change our intelligence. That's why we're here. So that's that's one of the things that really gets me is the stuff on intelligence quotients. And so what they did is these people who came up with it, evil people, I say, they say that the average intelligence is 100. If you've got 100, your IQ, you take an IQ test, you've got 100, you're considered right in the middle, the mean. Okay, and the thing is they make these tests up, right? They're culturally biased, they're racially biased, they're just biased. Okay, I know I'm biased too, but at least I admit it, right? We're all biased, so let's use it. Okay, so but standard test scores have a standard deviation of 16. So again, we just write that down. We've got a mean of 100, standard deviation of 16. And so then what would data value be if we had a z-score of negative 1.5? Well, we know it's going to be below 100, right, because it's negative. They're going to walk through this. What I'm going to do is since you've got it all here, right, you would take your mean minus the score, z-score, times the standard deviation, and that's going to give us that it would have been a IQ score of 76. But let me show you this in general. Remember, z-scores equal data value minus the mean times the standard deviation. So what we do is we do some algebra. You don't have to do this because we just do it once and we'll get a new formula. So we multiply by standard deviation on both sides. Okay, standard deviation divided by standard deviation. So we get z times the standard deviation equals the data value minus the mean. What they did next is they add the mean to both sides because what we want to do is have a formula that tells us what the data value is. So we'll add the mean to this, and again, there's no like terms. What they do is they put it in front so that if the z value is negative, it just looks nicer. So I'm going to write it down here because this is, again, another standardized formula that you can just kind of have ready for you. If you take the mean plus or minus, depending upon the value of z times standard deviation, that's going to be your data value. Okay, and remember so we've got these two formulas. We've got this one, and so this is if they give us a standard score and we want to find the data value, we use this. If they give us the data value and we want to find the z-score, we use this one. Okay, so we've got the two formulas. We can go back and forth between a data value, a standard score, and a data value. Okay, but bottom line is that would be a IQ of 76 and 1.5 standard deviations below. Now, I'm not saying that there's sort of a limit. I won't even tell you I'm close to being a genius or that I even feel like I could become a genius, but I'm okay and I get by. But there are also some stupid things I do. So I don't know, intelligence, it's really situational. You have to judge it, when someone does something really, how do smart people do crazy things at times? Intelligence seems to be one of these things that comes and goes. So you'll hear me talk about this because the normal curves, especially when they apply to education, because remember the normal curve comes out of sort of a thing that's probabilistic. It's from probability, and I I want to believe that education is not a game of chance, that we just throw students in a classroom, we give them a few books, give them a teacher, and well, some will learn, some won't, but it's just a crapshoot, right? I can't believe that. I got to believe that the teacher, the student, we all make a difference between about because of the effort we put in. Um, we have what ability? I know we have certain limits. You see me when I work things. I do tend to transpose numbers. I there are certain things, but using the normal curve for education, I think is almost criminal. Okay, so but we'll work the problems if we have to, right? So percentiles, another way we could divide this up. So that's 68, 95, and 99.7 rule. That's by making divisions every standard deviation. This way kind of goes with thinking, because remember, in the middle, this could be the mean, but it's also the median. So if we want to think of the median, the way they divide things up with the median is they go percentage of data. And so they make it into quarters, fourths. So 25%, 25%, 25%, 25%. And so this would be your first quarter of your data. Notice it's not equally distributed necessarily, not equally by this distance down here. So here to here is a lot more distance, is a larger range. Let's use some statistics. It's a larger range than the distance between this quartile, right? You can see that right there. But the amount or the percent of data in each of these quartiles is the same. That's what a quartile means. It has exactly 25% of the data in it. But this, again, the measurement, the data values that would give the bottom 25% are more spread out than the data values that would give the central 25%. Okay. And so then this one's called the third quartile because you've got 1, 2, 3 by the time you get there. We could call this the fourth quartile. Sure. Here we could call the median the second quartile because there's 1, 2 quartiles to get there. Okay. So there's it's a 25th percentile so a percentile is percentage of data. Quartile is a fourth of the data. Okay. So 50th percentile. And percentile means that's the percent of data that's below a particular number. Okay, so be careful. I remember maybe it was my intelligence quotient or something. And I don't know, I heard my dad saying something and I was in the 10th percentile. And I was so proud of myself because I thought, I don't know, third grade, fourth grade. I'm in the 10th percentile. Man, I'm smart. Because, of course, in my mind, I'm in the upper 10. But what is the 10th percentile? It means you're the bottom 10. No shame in that, but at least know what you're talking about. Who cares? Third grader can do whatever they want. But percentile means percent above. So you want to be like in the 95th percentile. That means you're, above 95%. 10th percentile means that actually there's 90% above you. So again, nothing wrong with it. We all got to be somewhere on there, and I own it. I'm 10 percentile. I can't even remember what it was for. Probably I was kind of a chunky kid. I was slow. I was probably in the, we had that President's Physical Fitness. Do you guys still do that? And you had to run and all this stuff. I didn't like to run. I was a slow kid, and I did it on purpose. So I said, I don't like to sweat. So I think that's what it was. But anyway, percentile is percent below. Okay. So I guess, sorry, you guys. You can always fast forward, but it's like, I don't know, I'm realizing it's our last night together, and I've missed, I only got half a semester with you all. And maybe not even that because it was late start, but I do appreciate your energy, and I appreciated this opportunity to work with you, and hopefully these videos are helpful for you and you're getting some good success. Okay. So percentile interpretation for z-scores. So the easy one is a z-score of 0. That's right in the middle. That's always at the 50th percentile, right? So 50% of the items are below. It's also 50% above, but But that gives you, once you know what percent's below, you subtract from 100, you know what's percent's above. So if you're in the 60th percentile, that means 60% are below, but 40% are above. Does that make sense? So the 60th percentile would look something like this, that this area would be 60%. So this area has to be 40%, because the area itself is all 100%. There's no more than 100%, no less either. Everything is accounted for. Okay. And again, the mean, the median, and the mode are all the same. So I'm not going to worry too much about this. I'm not sure if I even gave you problems on this, but I did want you to know that margin of error, what this tells you is you use the sample size. How many people did they survey or measure? That is the sample size. So the margin of error is, again, this is plus or minus. So it's whatever you measured. Say you measured 25% of the people say they're ready to go back to school, whatever they want to say, 25. There's always this margin of error. And the more people you ask about their opinion, the larger this number is. Notice the smaller the error is going to be. The margin of error will get smaller as you ask more people. So you ask 2 people, it's not going to be very, that's 1/2, square root. Actually, you ask 4 people, square root of 4 is 2, that's 1/2. That's 50% margin of error. I wouldn't trust a study that had a 50% margin of error, because you add that and subtract that, it means, well, it could be 0% or it could be 100%, somewhere in between there. That's not very helpful. So n equals 4, not a good study. Because it's going to have such a large margin of error. But what you'll see is the more people that ask, the larger the sample, the smaller the margin of error. Okay, so we've got this random sample of 1,172 children. What does that do for us? They measure and they found that 17% of the children said that they get bossed around is a bad thing about being a kid. So only 17%. I don't know. My neighborhood, we're always getting bossed around. 17%. But what does that really mean? Because this is all the people we asked. So we're going to find the margin of error. So n is all the sample size, 1,172. Take 1 over the square root of 172 times 100%. We've got a margin of error of almost 3%. So it means 17 plus, so it's like 20% down to, take 3 away from that, is going to be 14%, 14 to 20%. So you really can't, whenever you hear 17%, what you want to think is, what's that margin of error? In this case, the true answer is somewhere between 14 to 20%. That's, and again, they, 2.9, they get down to it. I like just 14 to 20. That's good. It's good enough. Of course, my reporting had a margin of error as well, but we're all good. Okay. So just think, whenever you hear a statistic, there's got to be this margin of error. And it all depends upon how many people did they survey. They surveyed 30 people, it's going to have a fairly large margin of error. They did 10,000 people, that's going to be a much smaller margin of error. Okay, so some other kinds of distributions. There are ones that are skewed, like this one, where the mean and the median and the mode are different. So whenever the median and the mode are below the mean, we get this kind of a skewing, which they call, they call this one skewed to the right. Now, I have a hard time with this because I see this bulge to the left, but what you count is where the outliers are. So this is what? Weekly earnings. Remember, once you get to 0, usually you can't have negative earnings. Now, you might be spending more money than you're getting, but you usually can't earn negative money. So there's kind of an end point here, but some people get paid an incredible amount And so there could be these people, $1 million a week or something that are way out here. So that's skewed to the right. So the tail is to the right. That's when we talk about skew, we look at the tail. Okay. So this is not a normal distribution. We can't use all the stuff we've been doing. There's other tools. And if you take a statistics class, you'll look at something like these. I think there's a chi-square distribution, and it's got a particular type of a skew. But anyways, you've got other distributions that can be used. So now what we're going to look at is we're going to take these concepts we've talked about, we're going to apply them. And we're going to calculate some z-scores. We're going to find some percentages and some percentiles, if you will. Okay, so just do some applied problems. Nothing really new, just applied. Okay, so first, finding the percentage of data items less than a given data item. The percentage less than the value. Okay, so this is what we're finding is the percentile. What percent are below? Okay, so in this one, we're told that for men between 18 to 24 years, they have a mean Department of Health at cholesterol levels 178.1. Standard deviation is 40. So again, I like to just come over here. My mean is 178.1 and my standard deviation is 40.7. Write them off to the side. What percentage of men in this age range have a cholesterol level less than 239.15? Okay, what is this? This is a data value. Okay, so first we go about the z-score. So here z is the data item minus the mean divided by the standard deviation. So they just fill in those things. The data value goes first, the mean comes over here, and the standard deviation is what we divide by. So we do the calculation and we find it has a z-score of 1.5. So if you remember I like to draw these little bell-shaped curves, sort of. So there's our mean. 1.5 means it's above, and here's 1 and here's 2. So 1.5 is like this. What we're trying to find out is what percent is back here. Now we had between -1 to 1 was 68, between -2 to 2 was 95, and between -3 to 3 was 99.7. So how do we go about this one? Well, we look it up on a table. Okay, I'm going to show you the full table, but what we do is we're looking for 1.5. That's our data value. The table will tell us that that's a percentile of 93.32%. So let's back up. What we could say is that this area is 93.32%. Okay, perfect.